Thank you very much to the organizers, first of all, to Danielle and Jesse and the other organizers for inviting me to give this set of lectures. I'm very honored and I'm very excited to speak to this diverse crowd of people. I see from the chat that there are students really from all over the world, and that's always nice. On the other hand, I know that the organizers had a bit of a selection process. I was not entirely sure, what the level of the students would be. So I made some estimate of what the level of students would be, and based on that, I've prepared some lectures. But if I'm going too fast or I'm going too slow, I would very much appreciate if you were to, just ask questions and stop and ask. And I think that would be very helpful, particularly in a Zoom meeting. I think, the more participative it is, the better it is. And if you have a question, it's probably quite likely that other people in the audience have the same question. So, please do ask. This course is about the information paradox. But I thought I would start. So, roughly, I'll give you a sense of how I'm roughly planning to organize this. So my idea is, this is so the idea is that today, we'll just have an introduction to black holes, classical and quantum properties. And then we'll do an introduction to the information paradox somewhere here. Probably already in the first lecture, but, going into the second lecture, I'm guessing. Then I want to discuss, some aspects of pure and mixed states. And their statistical properties. And then I want to spend some time discussing, the unusual localization of information in gravity. Because I think that, one of the key things that we learned from the information paradox is that quantum gravity, localizes information very differently from ordinary quantum field theories. And I think that's, one of the key physical lessons that comes out of the paradox, and also one of the key takeaways that we should have. And then I want to discuss finally some refinements of the paradox. If you have time, and this will include, questions about fuzzballs and firewalls and so on. And if you have time, we can go into as much depth as we want. Yeah. So that's roughly the outline of how I'm planning to proceed. As I said, this is a dynamical outline. And if you tell me that I'm going too fast or I'm going too slow, we can modify this. This is not set in stone. And it's important, I feel, that the objective of these lectures is that you should learn something about the subject. It's not that these 5 lectures will teach you everything you need to know about the information paradox, but provided you learn some interesting physics, and I'll try and persuade you there's a lot of interesting physics to be learned, I would consider that a success for this course. Okay, so before we start...
Sorry,
yeah.
Someone asked, will you discuss open questions as well?
Yeah, in some sense, a lot of what we are going to discuss corresponds to open questions. Maybe the first lecture, the things I'm talking about are, very well known and were established, 50 years ago. Already, from the second lecture, when we start talking about pure and mixed states, there are slightly different perspectives in the literature and their statistical properties. But this is also, I suppose, pretty well established. And then, some of the recent work I'll talk about in the unusual localization of information is really work that's been done in the past few years. I'll discuss what is known and what is not known. And by the time we are discussing refinements of the paradox, there are some questions that clearly haven't been addressed. So, this whole field is a modern research field. What everyone agrees on is basically the stuff I'm planning to discuss in the first lecture. And already beyond that, we'll be having slightly different people have different perspectives. So you can consider a lot of that topics of modern research and not even necessarily topics of agreement. Are there any other questions about the outline before we proceed?
Is this the 5 numbers, each of them for each class, or it's like a mix?
Is this the outline for everyone? Roughly, I suspect I'll probably do some introduction to the information paradox today, and so I might do some of part 2 already in lecture 1. But roughly, approximately, this is how I'm planning to do things. I might get to point 4 already in lecture 3, but it really depends on how many questions there are and how fast we go. So I don't have a as I said, this is a dynamical outline, and I'm happy to modify it. My plan is roughly to follow this, but maybe get to lecture point 4 already by lecture 3. Interesting. Are there any other questions about the outline, or maybe we'll proceed then? Okay, as I said, it's not important that everything I convey you're able to understand perfectly, but it is. I would really like you to understand some of the basic physics of what we're talking about. So at least next time you attend a seminar on the subject, you're in a position to participate in it meaningfully. Yeah. Okay, so let me start by discussing now the topic of black holes. Okay, so I'll start by drawing a Penrose diagram of a black hole, which I presume is something that you've all seen, because Daniel just told me there was, all the students here have taken GR. So, the way we draw this Penrose diagram is there's some infalling matter, and this is the way it's drawn. Okay. So this infalling matter could be, some massive field. So it starts from past infinity. It doesn't actually matter what this infalling matter is doing. This null line is what's called the horizon. Okay. This line is called the singularity. Okay. Is this diagram familiar to everyone? And this null line is called scri minus, and this line is called scri plus. Yeah. So I'm assuming that all of you have seen some version of this kind of diagram. It's called a Penrose diagram. It's a diagram where time goes up on the y-axis and space is on the x-axis. I've suppressed at every point an S2, so there's an S2 at every point. But other than that, this is showing how space and time evolve. This is a cartoon, of course. This is not something, doesn't correspond. This diagram that I've drawn, there's no specific profile of infalling matter that I've taken, but it roughly tells you the correct qualitative features of what happens when a black hole collapses and what the space-time looks like. Also in these Penrose diagrams, some coordinate transformation has been performed to bring all the coordinates to finite ranges. So is everyone on board with this, or are there any questions about this Penrose diagram? Okay. Okay, sounds good. So now, what do we want to do in this Penrose diagram, right? All of this lecture is going to be about some region of space-time that's here. Okay. So our lectures are about this region of space-time. Okay. What is this region of space-time? Okay. This region of space-time is about some region of space-time which is close to the horizon. So this is, some region near the horizon. And it's well after the matter has fallen in. So, there are other regions of this black hole geometry that you could look at. For instance, you could look at this region of the black hole geometry. This region of the black hole geometry is where the matter has collapsed and where the matter has just crossed the horizon. And that's an interesting region of the geometry to look at for different questions, but it's not the region that we're interested in. That region is highly dynamical. It's when the geometry hasn't settled down. It depends on what the infalling matter was. If you go to my astrophysical colleagues in the next office, just give me 1 second, please, 1 second. So, sorry for the interruption. This was a tech problem we were trying to solve, which finally got solved. Yeah, so as I was saying, if you go to my astrophysical, my colleagues in the next office, you will find that a lot of their discussion is in fact about is about this region of space-time, right? What happens when black holes form, when black holes merge? It's not really about the time well after when all the matter has fallen in, but rather it's about the time when matter is falling in and dynamical things are happening to black holes. But that's not what we are trying to discuss. Yeah, we are also not going to be interested in these set of lectures about what happens at the singularity, and partly that's because very little is understood about what happens at the singularity. So this is already to some extent a matter of perspective. But at least the perspective that I'm going to present in these lectures, and this is, I suppose, a perspective that a majority, but not all researchers in the area have, is that many aspects of the information paradox can be understood without asking what happens at the singularity. They have to do with what happens in the weakly curved spacetime. So we are going to be discussing, and that's why this region is important. So it's some region, as I said, that's well after the matter has collapsed, when things have become quasi-static, but which is far from the singularity. And in general, the kind of black hole that we'll be discussing is a black hole which is a very big black hole, so that this region looks a lot like flat space. And in fact, I'll make that precise in these lectures. I see there's a question which says in the Penrose diagram, there's a hidden spherical symmetry. Yes, that is correct. In this Penrose diagram, at every point, there's an S2. It does not matter qualitatively if the black hole is not spherically symmetrical. The Penrose diagram that we would get, you see different kinds of Penrose diagrams for black holes which are not spherically symmetrical. But for the kinds of questions that we are asking, it is not believed to be very important. What happens if the black hole is not spherically symmetrical? One case we won't discuss in so much detail is the question of what happens when the black holes become extremal. But as long as we are not in that limit, if you just had some rotation or some charge or some other, some electric charge or some other charge, it is not going to affect the qualitative aspects of our discussion. Are there any other questions about this? Okay, good. So let me, the full metric. So the first point I want to make about this is that the full metric of the space-time is actually a pretty complicated metric, right? This kind of metric can be studied. It's not like we cannot study the full metric of the space-time. This kind of metric was, first studied by many people. In fact, physicist called B. Dutt, although whose work was not known widely until much, was not noticed widely until much later, but was one of the first people to study this, and then Oppenheimer and Schneider. Okay? They studied these kinds of metrics, and there's a simpler version of this collapse, which corresponds not to this kind of matter that I've drawn, where I have some massive matter that's collapsing, but to a null ray that collapses and forms a black hole, and that kind of collapse is called Vaidya collapse. And so, you can study the full metric that you have here, where you start with something in empty space, you really send in something from the far past, that thing collapses under its own, gravitational interaction to form a black hole. That can be done, but that is in fact not what we are interested in. Okay? So the full metric, as I said, can be studied. If you are interested, you can look at these kinds of details. But as I just explained, we are not interested in that, because the details of these full different metrics, they differ in what happens when the black hole is collapsing. What we are going to be interested in is, in fact, what happens as t tends to infinity. Right? And by the way, when I say infinity, as we will see in a minute, this infinity corresponds to a classical infinity. In fact, in the quantum theory, not in a minute, as we'll see in some time, in the quantum theory, once you turn on quantum effects, you find that after a very long time, the black hole in fact starts evaporating. But in the classical theory, if you just wait for very long times, then you find that the metric takes this form. Okay. And this function, as I said, this metric is something that's spherically symmetric, which I've taken to be spherically symmetric. And this function has the form. Okay. This mu is the mass parameter. And in fact, it's related to the physical mass with some set of factors that will never be important for anything we are saying in this lecture, but let me just write them down. Okay. Okay. And in particular, the radius, the horizon, okay. This black hole, by the way, lives in d+1 dimension. So everywhere you see d appearing here, this is the dimension of space. If you've seen, black holes that appear in, if you've seen black hole discussion only in 4 dimensions, you're welcome to put d equal to 3 everywhere. In which case, RH is just proportional to, where the horizon, RH is just equal to this mu, and you'll find this factor just becomes the factor of 2, so that this mu is just related by a factor of 2 to the mass of the black hole. But you can also write down these formulas in general dimensions. Yeah. And as I said, when we say t goes to infinity, we mean something specific. Means that you see the scale in this problem is RH, means that t is much greater than RH, but t is much smaller than the evaporation time, which we haven't specified, but we will specify soon. Okay. So this is the classical geometry, and this is the first thing that you should know about this system. Are there any questions about this? Okay, let me now introduce a slightly different coordinate system that's already useful to understand this geometry. And it's kind of an important preliminary to understanding the information paradox. So it's often convenient to move to what are called tortoise coordinates. What is the evaporation time is the question. Yeah, evaporation time is a concept that we haven't introduced, but as I said, we will introduce it by the end of this lecture. It's once we turn on quantum effects, it turns out that the black hole starts evaporating. So this is, if you take a black hole and you don't have anything around it, it starts evaporating, and eventually it evaporates completely. In fact, the information paradox is a discussion of what happens to the black hole after it evaporates and the information that was in the black hole after it evaporates. And so this evaporation time is some time that I'll specify. All that's important at this point is that this is the form of the metric for times which are much longer compared to the time of collapse, but much shorter compared to the evaporation time. Yeah. Okay. So these tortoise coordinates are defined by d of r by f of r. Okay. These are just some useful coordinates. And if you, whether or not I'm able to convey much about the information paradox, this is just some basic technique that's used in understanding black holes. And these coordinate transformations and so on are just things that you should all be familiar with. So I hope I can at least convey these things. Yeah. So we want to understand, how r star behaves as r tends to infinity and as r tends to RH. Okay. So near r tends to infinity, if you look at the form of f of r, let me just show it to you again. You see that f of r just becomes 1 because as r tends to infinity, this factor goes to 0, whatever the value of m is. And so dr star tends to dr. If that happens, you're basically, so you're forced, so, or, you can, unless you add some infinite constants, and which we don't. So as r tends to infinity, r star tends to infinity. Okay. What is the region where r tends to infinity? And if you go back to this Penrose diagram, this is the region where r tends to infinity. It's the region very far from the black hole. This is the region where r tends to infinity. Okay. Okay, so that's what happens to R star as R tends to infinity. It tends to infinity itself. The more interesting question is what happens. The space-time dimension is d plus 1, and d is the spatial dimension. Yeah, and what we are writing. There was a question in the chat. Yeah. So okay, as R tends to RH, okay, you see that f of R becomes equal to twice kappa into R minus RH. Okay, and this constant k here, I mean, just by definition, so it tends to. This constant k here is just f prime of RH by 2, right? We are just doing a series expansion of f of R near R equal to RH. You can see that at R equal to RH, by definition, this f of R vanishes, right? That's where the horizon is at. And you see it when, I mean, because it's defined to be this, when you set R is equal to RH, this factor becomes 0. So the horizon is a place where f of R becomes 0. Therefore, if you're slightly outside the horizon or slightly inside the horizon, you expect that f of R takes on some linear form. And I'm just calling the coefficient of that linear form kappa or k. This term will be important to us, and this is called the surface gravity. I don't want to get into here about why it's called the surface gravity, but it's, for our purposes, it's just f prime R by 2. Okay. So now near R equal to RH, as R tends to RH, we have, dr star is equal to dr by twice kappa into R minus RH, right? Is that fine? Okay. So you can solve this easily, right? And the solution is, just after you put in some constants, it's 1 by twice kappa into log of R minus RH into twice kappa. There are two twice kappas here. This guy was fixed, right? This guy came from the solution of the differential equation. Because, the differential equation told us what dr by dr star was, and the coefficient of that is fixed. This twice kappa is something we added by hand. We added by hand, just to make life a little convenient for us. We could choose something else, but, we chose this. And with this convention, we have R minus RH is 1 by twice kappa into e to the twice kappa R star. Okay. And in particular, as R tends to RH, R star tends to minus infinity. Okay. So this behavior of this tortoise coordinate, which basically goes from minus infinity at the horizon to plus infinity as we go off, to infinitely far space, is the behavior that you should always be familiar with. Yeah, the question in the chat about whether the tortoise coordinate transformation is valid at R equal to RH. No, the point R equal to RH is slightly singular for this, and we will discuss in a minute what are the good coordinates that you can use to cross the horizon. You can see that this is the case because this coordinate is going off to minus infinity at the horizon, right? So you've kind of reached the end of its range. So indeed, you have to do something different when you cross the horizon. It doesn't mean anything bad is happening at the horizon. It just means that in this coordinate system, this coordinate system is reaching the end of its limits at the horizon. Yeah. Okay. Are there any other questions about this? Okay. So in terms of R star, you see that the metric reads just as now. Here I wrote R and here I wrote R star, and this R you can think of as a function of R star. Okay, so you can solve this was not an equality. This okay. So just to emphasize, these equations I wrote above were valid near R equal to RH, and that's because this is what was happening as R tends to RH. Okay, so this was as R tends to RH on the previous page. This is not always valid, of course, because in general, the form of f of R is more complicated, right? So this linear form only occurs very close to R equal to RH, and all these formulas are valid near R equal to RH. But in general, R is always a function of R star. You can always write R as a function of R star. And what appears here is always r squared d omega squared. Okay, it's not r star square, r squared d omega square. That's not a problem because you can always in a metric have functions of some other coordinates. And in fact, the spherical part of the metric won't be so important for us. Okay, the important part is by making this transformation, we pulled out this conformal factor here, and the rest of the metric looks like minus dt square plus dr star square. Yeah. Okay, are there questions about this? Okay, good. Now, there was a question in anticipation already about what happens as we cross the horizon. Okay. In fact, to cross the horizon, what you should do is you should move to a slightly different set of coordinates. That different set of coordinates are called crucial coordinates. Okay. And the crucial coordinates, you can just think of minus t. Okay. Okay. So these coordinates have the property that, if du is just equal to just by differentiating, there's some factor of kappa that just gets cancelled out. Okay. And dv similarly is equal to dt plus dr star into e to the kappa into r star plus t. Okay. And remembering, the formula that we had earlier, right? Remember, if I now multiply du and dv, you see here you have e to the kappa r star minus t. Here you have e to the kappa r star plus t, right? If you multiply these two, the minus t will cancel and you'll get e to the twice kappa r star. Notice this is the factor that you had here, which was e to the twice kappa r star, right? So, there's also some factors right? So when you do this, you will find that ds squared takes the form minus du dv, okay, plus r star d omega squared near r equal to rh. Okay. So these coordinates are good because they tell you that, the metric near r equal to rh is almost identically like, almost exactly the metric of flat space. Of course, as you go away from r equal to rh, this is not the metric everywhere. But if you're right near where you are, right near flat space, right near the horizon, then you see that, there's nothing singular that's happening at the horizon. Rather, if you work in terms of these coordinates, du and dv, which are some null coordinates near the horizon, then the metric is just perfectly regular, okay? And it just looks like minus du times dv, okay? In this language, the horizon is at u equal to 0. Okay? So the horizon is just a null ray and it just sits at u equal to 0. Okay? And you can check that in this horizon, if you look at t is proportional to log of v by u, and this tends to infinity at the horizon. Okay? So just to recap everything I've said so far, let me draw the horizon. Okay? This, as I said, is the region we are interested in. Okay? This is the horizon. This part has r star tends to minus infinity, t tends to infinity. Okay? This part has r star tends to infinity and t tends to infinity. That's what's happening here. In these crucial coordinates, u tends to 0 here. Yeah. Okay. Are these set of coordinate transformations clear to everyone? This might be a review for some of you. But can we just multiply differential forms like this? Sure. You mean this? Yeah. I mean, you can write it in terms of just taking derivatives, but sure. Yeah. Why not? Yeah. I mean, these are just some functions, right? So u is some some function of k star and r star, and sure, yeah, you can do this. Are there any other questions about the set of coordinate transformations? I mean, this is just calculus. I'm not doing anything very fancy here. I'm just trying to ask, if you make a small variation in t and a small variation in r, how much does u change? And it changes in this way that you just get from the fact that u is this. So this is just calculus. There's nothing fancy, in fact, here about. I mean, this is just there's nothing fancy that was used here. It was just saying a small change in t, a small change in r leads to this change in u, and this is how these changes are related. Okay, are there any other questions here? Okay, now the thing is that you can introduce in this part behind the horizon here, behind the horizon, we can introduce another set of coordinates. Yeah. And you can introduce another set of coordinates, right? And these are defined in the same way that we had previously. There's another tortoise set of, another coordinate patch. And this coordinate patch has the property that, behind the horizon, this tortoise coordinate also tends to minus infinity, t also tends to infinity, except that the relation here is now this. There's a minus sign that's missing. Okay? So u is now positive behind the horizon and v is just continuous, okay? So what changed, the coordinates u and v are continuous. What changed was the relationship between u, r star, and t, because u crossed 0 across the horizon. But, with this relationship, which, you can always define now for u positive, another set of coordinates, r star and t. And so going back to this diagram, we again have r star tends to minus infinity on this side, and t tends to infinity. Okay, so t tends to infinity both sides, behind the horizon, in front of the horizon. But there are two places where t tends to infinity, as you approach the horizon from the outside, as you approach the horizon from the inside, and r star always goes off to minus infinity. Remember, of course, that if you give me a value of r star and t, I have to tell you whether I'm outside the horizon or inside the horizon if I want to use these r star t coordinates. If you're using u, it's completely unambiguous. Yeah. Okay. Let me also notice something. Let me also point out something which is also a trick to compute change of coordinates. Yeah. Okay. Let me also point out something which is curious, which is that for r smaller than RH, f of r changes sign. That's because f of r goes to 0 at r equal to RH, and therefore when r becomes smaller than RH, f of r, which was positive earlier, becomes negative earlier. But the metric, remember, had the form minus f of r into dt square plus dr square by f of r. And so t becomes a space-like coordinate. And r star, or r, becomes a time-like coordinate. Okay? This is not something that's mysterious. Sometimes people say, oh, space and time flip signs behind the horizon and whatever. This is just something that's happening in this particular coordinate system. Okay? If you define a Kruskal time, which is v minus u, and x is equal to v plus u, everything is perfectly well defined. Okay, this is sometimes called the Kruskal time. This doesn't flip, right? Nothing happens. And this you can define as some Kruskal x. This doesn't change sign or anything like that. So the fact that this is happening in this coordinate system is not something that's mysterious or something that's deep or something that's physical. If you read science fiction stories, you will find that there's something very, very funny that happens behind the horizon, which is space and time change their roles. But that's not happening. Okay, it's not that space and time are changing their roles. It's just that we happen to have some coordinate system, and the coordinate that we were calling a time coordinate now becomes like a space coordinate, and the coordinate that we were calling a space coordinate now becomes like the time coordinate. This tells us about our choice of coordinates, not about something physical that's happening. It's not like space is becoming time. Okay? It's just that the coordinates we are choosing have this funny property. Nevertheless, since we'll work in some specific coordinate system, we'll have to be careful about this property. In the equations that we write, we will have to be careful about this fact, and so you should remember it. But you should realize that this fact by itself is not telling us that, something very complicated is happening. Okay, so that's what I wanted to tell you about the classical geometry of black holes. Let me just recap what I said so everyone is on the same page. As I said, it's possible that this is a review for many of you. I'll just recap all the points I've made. I said that, this is the Penrose diagram of a black hole. We are going to be interested in these lectures in this region of space. This region of space is a region near what's called the horizon of the black hole. It's a region that we're talking about, which is much later than the collapse time of the black hole, much earlier than the evaporation time of the black hole. The full geometry that corresponds to this collapse is complicated. It has many features. You can work it out in detail, but we are not interested in what happens to the full geometry because we want to look at this limit that t tends to infinity. The metric tends to this this simple form, universal form at late times. In this universal form, we have some coordinates which look like t and r. It's convenient to go to a different set of coordinates which look like r star and t. If you do that, then you find this picture, which is that this coordinate r star goes to minus infinity, t goes to infinity. On the other side of the horizon, you can introduce another coordinate patch. Again, r star goes to minus infinity, t goes to infinity. Okay, but there are some coordinates that are perfectly regular. Those coordinates are called Kruskal coordinates. They're related by some exponential factors to e to the kappa r star minus t and e to the kappa r star plus t, which are u and v coordinates. In these coordinates, the horizon is at u goes to 0. There's another coordinate v, which just increases regularly across the horizon, and u goes from negative to positive as you cross the horizon. So that's something that all of us should know about the classical geometry of black holes. Are there any questions about this part? Yeah, there's a question about what happens to v equal to 0. In this Penrose diagram, we don't see v equal to 0. If I were to draw the past horizon, and sometimes we discuss an eternal black hole, then that would correspond to v goes to 0. So there's another horizon which corresponds to v goes to 0, which is somewhere here. Okay, but in this set of lectures, we'll never encounter this v goes to 0 region. Yeah. How do we correlate these coordinates with those of the infalling observer? So the coordinates of the infalling observer are roughly related to these coordinates t and x. Now, if you really wanted to set up a coordinate system, then you'd have to specify how the infalling observer sets up their coordinate system. But if you ask, for instance, you take a geodesic and you want to ask what happens to the proper time, you can compute that the infalling observer will cross the horizon in finite proper time. These t and x's you can think of as reasonable proxies for what happens to an infalling observer. Of course, if you want to use geodesic time, the relation is slightly different. It's not exactly this t and x. But the point is just that the horizon is has some finite coordinates in the infalling observer coordinate system. Are there any other questions? Okay, so I'm guessing everybody is on the same page so far. The next thing I want to discuss is the propagation of fields. Yeah. Okay. So consider that there is some field. For a minute, I'll just make it a field which is a free field. Although I'll explain in a few minutes why. It doesn't actually matter for the discussion whether the field we have has interactions or not. In fact, a general field will have interactions, but those interactions will turn out not to be important. Okay, so let me think of a free field which satisfies some massive Klein-Gordon equation. We always like to deal with scalars because they avoid the complexities of trying to introduce spin in these geometries. You can, of course, do the same calculations with gravitons or fermions or gauge bosons and so on. But the properties of a scalar capture everything that we want to look at in terms of the physics of this. Okay. Okay. So remember that, this box guy looks like okay. So this box guy has some form which looks like this. Okay. So yeah, it's something that this operator is something that we can expand. And let me remind you, in tortoise coordinates, the square root g looks like f of r times r to the d minus 1 times some square root that comes from the g omega. This comes from the spherical part, and it's not going to be important. This also comes from the spherical part. Okay. This f of r comes because remember that the metric looked like f of r into dt squared minus dr squared. And therefore, if you look at square root of g, you just take the product of the lower components of the metric and you look at the square root, you get one factor of f of r sitting outside here. Okay. Okay. However, g star star, which is minus gtt, is 1 over f of r. Okay, that's the other factor that we need here. Yeah. Okay, good. So now we can write down what this wave equation is doing. This wave equation has some form, right? D minus 1, d star phi, right? Minus, right, just 1 second, please. Minus some 1 by f of r, okay, times dt squared phi plus 1 by r squared times box omega phi minus m squared phi is equal to 0. Okay. And this box omega is the sphere Laplacian. Okay. However, now notice something funny that's happening here. Remember, there's this factor 1 by f of r that's multiplying this dt square phi term and also a d star squared phi term. When you take this d star and you act on the r to the d minus 1, you'll get a factor of f of r that will cancel this f of r. But apart from that, you see there's a factor of 1 over f of r, and f of r is going to 0 as r tends to Rh. So as r tends to Rh, the wave equation becomes very simple. It just becomes d star squared phi minus dt squared phi is equal to 0. Independent of the spherical part of the geometry or what the geometry is doing on the sphere and so on. Okay. Notice, by the way, that what I'm saying here is also true in the presence of interactions. Okay. So this is independent of the angular part. Okay. It's independent of the mass. And also independent of interactions. Okay. So this is a very robust result about the behavior of the wave function as we go close to the horizon. Yeah. This is not something, I explained earlier that this is not something that was, the horizon was not a special place in space-time. And indeed, if you look at any null coordinate, you just draw a null line somewhere in space, and, you can introduce some analog of these coordinates, and you can find that, if you look at the wave function does have this part provided. You're very close to this null line that you have. Okay, so you can take any field, and the field has some simple behavior if you look at it in coordinates that are tuned to that null coordinate. Okay, and you're just seeing the same thing happen here. So in these coordinates r star and t, the wave function, the equation of motion takes on a very simple form. Is this clear? In particular, what this tells you is the following. This tells you that phi looks like sum of omega. There's an integral, of course, over omega, but I'm not going to be bothered here about the the precise measure factor, which of course you can write down if you wanted. Okay? So it looks like, oops, sorry, what happened? T. Okay, plus the Hermitian conjugate. And these guys are arbitrary functions on the sphere. And this is true as R goes to RH. Okay, so this is the behavior of the field as you go very close to the horizon. It's pretty universal. It doesn't care about what the mass of the field is and, what else the field is doing, what it's interacting with, and so on. And we'll see that this leads to some rather simple results for, correlation functions and other, aspects of the propagation of quantum fields. But these results, as I said, are rather general and very robust. If there were interactions, the Klein-Gordon equation would not be the equation of motion in the first place. No, that is correct. However, see what would happen here. You would add on this right-hand side some other term which would look like V prime R, okay, V prime of phi. Okay, so just follow this through. So what would happen on this side? You would get on this side, instead of 0, you would get V prime of phi. Okay? But notice that the V prime of phi does not have an F of R either, right? So as R tends to RH, it's still true that that term will drop out. So it's true that there will be a right-hand side of the equation. But, just like the M squared didn't matter, the V prime of phi doesn't matter either. So even if there are interactions, the important part that's happening here is that this F of R and this F of R are dominating. Yeah. And that, if there was an interaction, that F of R would still be dominating, and it wouldn't, the interaction would not be, would not change what we have just said. Is that clear? Okay. Are there any other questions about this? Okay. Now, what I've said here is that we have some arbitrary functions in the sphere. In fact, of course, it's often convenient to decompose things into spherical harmonics. Spherical harmonics, right? Which are some YL omega. And then corresponding to every such spherical harmonic, we have a complete basis of solutions. The basis of solutions looks like F in times some omega times some L times some R star times YL of omega. Okay. And then there is F of out times omega L R star times YL of omega. Okay. And this F in.
Can I ask a question?
Yes, yeah.
So this is a solution outside the horizon. So basically, I see that we have outside the horizon, we have solution of plane wave ingoing and outgoing.
Mm-hmm.
So what about if I solve inside the horizon?
We'll come to that. We'll come to that. For now, let's solve things outside the horizon, and we'll come to what happens inside. If you wait for a few minutes, I'll discuss that answer. Yeah. Okay. So, let me just say a little bit more about what you just said about ingoing and outgoing. That's a good question, but we'll answer it in due course. Right now, thank you also for clarifying. We are working outside the horizon. We are solving this outside the horizon. We can also solve this inside the horizon, and I'll explain what's different then. Yeah. And the boundary conditions that we put in this look like F in. We said this as R goes to RH plus. Thank you for clarifying that. Okay. I want this also to multiply e to the minus I omega t. So the t part is just e to the minus I omega t. And then there's a radial dependence of these modes. Okay. And the radial boundary conditions that you put are F in goes to some h of omega L times e to the minus I omega star. By the way, there's a raised hand by Juan Ramos. Did you already ask your question? Was this your question, or do you have a different question?
I think he has already asked his question.
Already asked his
Oh,
question.
sorry, it's another one.
Yes, the same question. Yeah.
Same question. Okay, right. Yeah, okay. Yeah, so yeah. Okay, great. So and F out, it has the form e to the I omega r star plus g omega L times e to the minus I omega r star. Now, this is something you should know about how waves behave in this background. So notice what we did. You see, we had these solutions, right, which look like e to the I omega star, e to the plus I omega star. Now, usually when we choose a basis of solutions, we don't choose the solutions that just look like e to the I omega star and e to the minus I omega star. Rather, you choose a linear combination of e to the plus I omega star and minus I omega star. You call that F out. You normalize the coefficient of e to the plus I omega star with 1. Then you demand that the Klein-Gordon inner product of this with this should be 0. So you look for an orthogonal set of solutions. That set of solutions looks like e to the minus I omega r star times h of omega L. Okay. Now, what is the property of this set of solutions? These ingoing solutions are pretty clear what they're doing, right? The ingoing solutions, F in has the property they're doing this. So the ingoing solutions you should really think of as solutions that just move into the horizon. Okay, that's because the ingoing solutions look like e to the minus I omega into r star plus t, right? So F in looks like e to the I minus I omega into r star plus t. When we talk about how waves move, we say that they move along lines of constant phase. Now, how should the phase be kept constant? Remember, as you go close to the horizon, r star tends to minus infinity, but t tends to infinity, right? So if you want to keep r star plus t constant, you just keep moving in this direction and you'll keep r star plus t constant, okay? Oops. What about the outgoing solutions? Well, the outgoing solutions have two properties, okay? They have a component that goes in, which is this component, but they also have a component that's purely outgoing at the horizon. In fact, these outgoing solutions are chosen as r star tends to infinity, F out just becomes e to the I omega r star. Okay. So it's chosen so that, you choose something which becomes e to the I omega r star as r star goes to infinity. There's some other factor you have to put in. I think the factor is r to the 1 minus d over 2. But other than that, you can solve this equation also as r star tends to infinity. And if you pick some particular combination of ingoing and outgoing solutions at the horizon, then you get something that's purely outgoing. And these are the modes that turn out to be orthogonal to each other. So you choose something that's purely ingoing at the horizon and something that's purely outgoing at null infinity, and that gives you a set of solutions that's orthogonal. I'll draw a diagram in a second. However, let me point out that this set of solutions does have an outgoing component also at the horizon. So F out, let me draw a different color, also has some modes that go like this. How do we know they go like this? Because once again, F out has modes which go like e to the I omega r star minus t, right? And e to the I omega r star plus t. These modes are just doing this, right? They're traveling in this direction because they're trying to keep r star plus t constant. The other modes which keep r star minus t constant, they travel in this direction. Yeah. Okay. However, these modes are chosen so that, they become purely outgoing at infinity. And here is how we should think of the whole setup. Okay. F in, we can think of as specifying data here. F out specifies data here. This is the horizon. This is cry plus. Okay. So if you tell me, if you tell me all the coefficients of F in, all the coefficients of F out, I've completely specified what the field is doing outside. Okay. Okay, good. So is this clear that, this is the solution of the wave equation? You can think of the solutions of the wave equation as specifying data, one part on the horizon, the other part at infinity. In fact, when you take an orthogonal basis of solutions, this is how you should take it. Take something at the horizon, take something at infinity. However, this part which is purely outgoing at infinity, it's not purely outgoing here, okay? But it does have an outgoing component also at the horizon. Okay. Okay. Are there any questions about this? Okay, good. No questions about this? Okay, good. Fine. So now let me say something about quantum mechanics and also about what happens behind the horizon, right? So quantum mechanically, we can just expand the field just by multiplying this with some creation annihilation operators. So we just write phi is sum over L omega R star, okay, B omega L times F in R star. You multiply the whole thing with e to the minus I omega t YL of omega, and then you write a Hermitian conjugate. Okay, so this is the expansion of the field. If you have a free field, this can be the expansion everywhere. Even if you don't have a free field, as I said, this expansion is valid near R, near the horizon. Okay, so A and B are annihilation operators or destruction operators. A omega L, B omega L, and A omega L dagger and B omega L dagger you can think of as creation operators. Right now, I've not been careful about how to normalize these operators because I've written sum here rather than integral. But that normalization will not be important. I'll tell you what happens when you correctly normalize the operators. The final result will present in terms of correctly normalized operators. Yeah. Okay, good. Any questions about this? Excellent. Okay, now there was a question about what happens when you quantize fields behind the horizon. So, of course, you can also solve this equation behind the horizon, and we can quantize fields behind the horizon itself. But there's an important difference. The difference is that behind the horizon, the destruction operators must multiply e to the minus I omega r star, okay? Not e to the minus I omega t, because as I said, this is a question of what coordinate system we are choosing. And behind the horizon, the time-like coordinate is r star. Therefore, the annihilation operators multiply e to the minus I omega r star. So we can write L omega I omega t omega. Whether you use YL or YL star is some choice of convention that makes things convenient later. This I'm calling A omega tilde, and then we can introduce another set of operators called C omega L, which looks like e to the minus I omega t times YL omega. Okay. Now this whole thing multiplies some other set of solutions, which I'll call F tilde out omega L R star, okay, plus HC, where this F tilde out omega L R star is a solution of the wave equation that has a property that as R tends to RH minus, it tends to e to the minus I omega R star, okay? And then I have to solve it forward in time. So, now R star is the time coordinate, and I've told you what it's doing as t tends to minus infinity or time tends to minus infinity, which in this case is R star tends to minus infinity. And then I have to evolve it forward according to the wave equation, okay? Is that clear? Okay. Now, as I said, we are never going to go deep inside the horizon, right? So we always remain at RH minus R by RH to be much smaller than 1. Okay. Okay. Now let me point out something which is true about the solution that we had, which is that notice that e to the minus I omega t plus r star is continuous across the horizon. That's because nothing happened, t plus r star takes on a perfectly finite value at the horizon. So e to the I omega t plus r star just is completely continuous as you go from outside the horizon to inside the horizon. Now, both outside the horizon and inside the horizon, we had these modes. Here, you can see that you have some modes which look like e to the minus I omega t into e to the minus I omega r star. Right? So these c omega l's can't be independent modes, and they must be related to the coefficient of e to the minus I omega t plus r star outside the horizon. This is true by continuity of the field, right? Because the field has to be continuous, it must be the case that, the modes that are continuous across the horizon are multiplied by the same operators on both sides. Therefore, c omega L, you can check, must be the same as a omega L into h omega L. These were some numbers that we introduced, plus b omega L into g omega L. Okay? But continuity does not fix a tilde omega L in terms of the modes outside. So, remember this, if we end up discussing refinements of the information paradox in lecture 5, this will be important that we have these modes inside the horizon that are not fixed in terms of modes outside the horizon. Okay? Okay, good. Are there any questions about what I said so far? So what I've done so far is I have, quantized the field both inside and outside the horizon. There was a question of what happens when you quantize the field inside the horizon. It looks very similar, except you have to be careful of, what you call the time coordinate. In this case, it's r star. It's not a t. And, you have to fix some parts of the expansion inside in terms of the expansion outside using continuity. But there are some parts that are not fixed. Okay? So just to recap what we did so far, I said the wave equation takes a very simple form. It takes this form here. The wave equation takes this form. You can solve it. You get some basis of solutions. The basis of solutions has two components, one which goes in here. Sorry, one which goes in here, one which goes out here. Okay. In fact, you can think of these components as specifying data on the horizon and as specifying data on null infinity. That's one way to think of what these different modes are doing. You can also quantize the field behind the horizon. You have to be careful that, in the coordinate system we are using, the coordinate corresponding to time is now different. It's r star, it's not t. Okay? Oops. Yeah. And, because of when you do that and you're careful of continuity, you fix half of the expansion, but you find that there are some new modes that are there behind the horizon. Yeah. Okay. Are there questions about this part? Or if there are no questions, I sometimes worry that I'm not being clear at all. It might be that all of you just know this, but this material that I just described is not always, it's taught in a QFT and curve space course. Maybe all of you have taken that, but if not, and if there are questions, I'd be happy to answer them. That question, yeah, a couple of questions. Yeah, go on, yeah.
I've got a question about the very first metric that we used.
Yes.
It was a metric about the horizon, near the horizon, and I mean that I understand that it is when the star collapse. It's that moment that we are studying that metric.
Yes. No. Sorry. Not when the star collapsed. You mean the first metric? After the star. That's why I emphasized. It's much after the star collapsed. We don't care what happened. You see, the region here is not near where the star collapsed. the star collapsed here. We are looking at
Yeah.
some region here. So it has
Mhm.
nothing to do with, you see, well after.
Mhm.
It's not where the star collapsed, it's much after the star collapsed. So it's not near, we allow the star to collapse and we wait. After some time, the black hole settles down, and that's the time we are looking at it.
So the form that we saw in that metric is an approximation to any form of the metric that any black hole?
Yeah, it's a certain spherical symmetry that's being assumed here. But it turns out that if you look at the classical metric of black holes, there's not too many different forms it can take at late times. At late times, the classical metric always settles down to something that's specified by the mass, charge, and angular momentum. And regardless of what the details of the initial collapse were, this is just a property of how the classical system behaves. Yep. And the reason it behaves this way is that if you have other perturbations which depend on the infalling matter, they tend to get radiated away. And so the horizon itself, in the case where spherical symmetry, settles down to this, or the region near this region that we are discussing. In the case where you have charge or you have some other angular momentum, it settles down to something else, but it always does settle down. We've made the assumption that the charge and angular momentum are zero. I could add them and then we'd get a slightly more complicated metric, but it is universal regardless of what the initial star was, if you look at this part of the spacetime. Oops. So there's some power problem here. I'm sorry, I'm here actually. It's gone dark. That's because there's some power problem here. I think it'll come back on. Yeah, go on, please.
One question. I don't understand all the detail why we have for the coefficient a tilde this matching, and for z we don't have. So maybe I guess that is because in upside we have
Yes.
two modes like ingoing and outgoing. So the ingoing we have in both sides, inside and outside. So this is maybe why we have this matching.
It has to do.
On the other hand, we don't have outgoing mode inside, so we don't have this matching for z. That's the reason.
No. You see, let's say you look at. Let me draw the diagram. Right here,
Okay.
You have some modes that are doing this.
Correct.
There are also some other modes that are doing something else. Okay. Inside also you have some modes that are doing this.
Yes.
But there are also some modes that are doing this. Okay? Now, you see, the white modes are continuous across the horizon. So they're the same modes on both sides.
Yeah.
These modes are not continuous across the horizon. So they're different modes on both sides. On both sides, you have a term that looks like e to the I omega r star plus t, and a term that looks like e to the I omega r star minus t. But it's the same term for the white modes. That's because of continuity of the field. Notice this expression is continuous across the horizon. Therefore, if you impose continuity of the field, that tells you the white modes are the same on both sides. That's because, you see, because t goes to infinity, r star goes to minus infinity. So t plus r star goes to some finite value near the horizon. And this, it labels different points on the horizon and it's continuous. On the other hand, the other mode, this e tilde mode, is multiplying e to the minus I omega r star minus t. Okay. So that's some rapidly oscillating phase. In one case, it's the orange mode. In the other case, it's the red mode. It's not continuous across the horizon. So that's why, we could relate. We have this relation for a tilde omega. So for C, which is fixed in terms of A and B, but a tilde omega is not fixed in terms of A and B. On both sides, you have two modes. It's not that there's, you have less degrees of freedom inside than you have outside. You see, the degrees of freedom have to be the same because the degrees of freedom are just fixed by local physics. Right? So, well, unless there are some boundary conditions that relate left and right movers. But in the absence of such boundary conditions, you have two modes inside, two modes outside. But the ingoing modes are the same. The outgoing modes are not the same. They're different because they're not continuous. So there's no principle that tells us that the orange should be the same as the red. But there is a principle, which is continuity, which tells us the white inside should be the same as the white outside. Do the tilde modes die out? Yeah, sorry. Yeah. Is that clear?
It is. Thank you.
Okay. Another question, do tilde modes die out at the horizon? No, it's not that they die out at the horizon. They oscillate rapidly at the horizon, and they will be pretty important in what we say. So it's not that they die out. It's just that the red modes are not continuous. They're rapidly oscillating near the horizon. And so there's no principle of continuity that will say the orange modes are the same as the red modes. In fact, it would give you the wrong answer. You know, if you were to try to set the orange modes in terms of the red modes and you computed the 2-point function across this geometry, you would get the wrong answer. So the orange modes explicitly shouldn't be the same as the red modes if you want this 2-point function to be a smooth 2-point function. Okay, are there any other questions? What if the metric is non-asymptotically flat? No, if the metric is not asymptotically flat, this is, I guess, about the earlier case of the metric. The metric I was discussing was the metric in asymptotically flat space. If the metric is not asymptotically flat, indeed, you will have to change the metric. So I won't discuss ADS, but in ADS, for instance, the change is very simple. It still takes the same form with f of r, except f of r has an additional factor, which looks like 1 plus r squared minus mu divided by r to the d minus 2. So you add a 1 plus r square instead of a 1, and then you'll get some metric that's asymptotically ADS. Of course, you could ask about other asymptotics, but the metric I wrote was for asymptotically flat space. Okay, are there any other questions? Okay, let me say something about, what these modes multiply. Okay, so, in terms of up to various constants, the a omega L, right, they multiply the factor that we have looks like u to the I omega by kappa, okay, plus some g omega L times v to the minus I omega by kappa, okay, up to constants. And then we have another term which looks like b omega L into v to the minus I omega by kappa. Okay, so the field looks like this. I'm not writing down constants here. I just want to emphasize what the different modes are multiplying. You see, one mode, which is the mode which looks like e to the I omega into r star plus t, is basically just v. Remember, what is this v coordinate? This v coordinate was just e to the kappa into r star plus t. So if I have something that looks like e to the minus omega into r star plus t, that's just v to the minus I omega by kappa. Okay, you see this? On the other hand, if you have something that looks like e to the minus I omega r star minus t, that looks like u to the I omega by kappa. Okay, so that's what these different modes are multiplying. They're multiplying as I said, the mode which is outgoing also has an ingoing component, which is multiplied by g omega L, but the field roughly has an expansion outside that looks like this. Okay. Okay. Now it turns out that we can define some near horizon modes, okay, that have the property, and now I'm going to state some results. Okay, I'm going to state some results, I'm not going to go through the details of all the calculations. These calculations you can find in many different places, but I'm just going to state some results because it's simple to, the calculations are complicated, but the final result is simple to state. So you can define what are called near horizon modes, and you define them in the following way. Okay? You take the field, you differentiate it. This is what's called a near horizon mode. Okay. You differentiate it. Okay. You just multiply it. You evaluate it at v equal to 0 at omega. Okay. And then you integrate it with some function of e to the minus I omega naught and some other function. This is just some function that, dies off at large u. It's some smearing function. Let me just explain what this function is doing. Apart from this smearing function, which is actually irrelevant, and so it's just required to make the mode normalizable. So forget about it. Okay? What this operator is doing is just taking u, differentiating it on the, on some surface, which is, it doesn't have to be at v equal to 0. It could be at some other value of v equal to constant. Okay. Sorry. Anyway, the integral is over u, so it just, it's some value of v equal to constant. You just take the field, you differentiate it with u, and you integrate it with u to the minus I omega naught. Okay? So it's like a Fourier transform of the field as a function of u. Okay? If you can think of it as a Fourier transform in log of u. Okay. So this is a mode that you can define. Okay. And you see that you can compute the 2-point function of this mode if you know the 2-point function of the field pi. Okay. Okay. It turns out that these modes, if you define, if you define ANH, just 1 second, let me try and get my factors right. Okay. Sorry, I'm just trying to get some factor right. 1 second, please. Yeah. If you define omega is equal to kappa omega naught, okay, then you will find that the 2-point function of this field, 2-point function of ANH, is fixed by the phi 2-point function. Okay. This phi 2-point function has a universal behavior if you're very close to u equal to 0. Why does it have a universal behavior very close to u goes to 0? Because that behavior is controlled by very short distance physics. If you're very close to the horizon, then you're controlled by what's happening at very short distances. And that's why if you're trying to evaluate this 2-point function at 2 values of u, which are just outside the horizon or just across the horizon or just inside the horizon, you can see that this 2-point function physically, you can expect that it has a universal behavior, because the short distance physics doesn't care about what's happening in the global part of the space-time. Okay? However, this behavior near u goes to 0 is enough to completely fix this Fourier transform, because u to the I minus u to the I minus I omega naught oscillates an infinite number of times near u as u goes to 0. Okay? So even if you choose to do this integral from u equal to epsilon to u equal to 0, this is almost completely sufficient to pick out, a particular mode in this field. Okay? You will find that if you do this, you can evaluate what the modes. So this mode is specified as some function of omega and of L. Omega is related to omega naught that appears here by this factor of kappa. And you will find that this 2-point function is, you can evaluate, and it turns out to have the following form. Okay. And this is just completely universal, and it's fixed by the short distance behavior of the phi function, of the phi correlator. Okay. You can also ask, how is this A omega related to the capital A omega states that we had earlier? Okay. Earlier, I also said, I asked how was, I defined some mode, some expansion of the field, which was terms, which was in terms of these capital A omegas. And it turns out, if you just do this carefully, you will find A omega L is A omega prime L times some Q of omega prime omega, where this is very sharply peaked around omega prime equal to omega. Okay. So these A omega modes are slightly smeared versions of the A omega prime modes, which are smeared in order to make them normalizable. Okay. And their 2-point function is completely fixed by the short distance behavior of the 2-point function of the field. And it turns out to be this 1 by 1 minus e to the minus beta omega, where this factor beta is related to the surface gravity by beta is equal to 2 pi by kappa. Okay. Okay. I said many things, and I skipped over many steps because I didn't want to do this detailed derivation. So I'm going to say the same things again, just so that we are all on the same page. Okay. So if you want to look at the details of this derivation, there are many papers where you will find these details. I can also give references in either to the organizers or next time when we join. Let me just emphasize what I said. I said, we had a field which we quantized, right? Then I said, you can take this field and you can do some process that basically just pulls out this outgoing mode of the field. Okay? How do you pull it out? There's some details in this formula. The details of this formula, however, are not important. Well, you integrate with a spherical harmonic to pull out a mode. There's some smearing function that's required to make it normalizable, not important. Okay? And then important in some deep sense, but not important for the basic physics. You have to differentiate the field. The fact that you have to differentiate it is not, again, crucial. And then you basically just integrate it with this mode u to the minus I omega. So what you're really doing is taking the field and trying to pull out the coefficient of minus u to the I omega. Okay. This coefficient, you can see, just pulls out, all these factors of TF minus u and so on, are just required to pull out a normalized version of these A omega operators that we discussed previously that multiply the outgoing modes of the field. The advantage of writing this mode in this way, earlier we wrote the field in terms of the modes. Now I've written a mode in terms of the field. The advantage of doing this is that you can now evaluate the 2-point function of the mode. You can write down an expression for A omega dagger, and you can evaluate A omega times A omega dagger. You see that gets related to phi of u and phi of u, the 2-point function. But you only need to know the 2-point function very close to u goes to 0, because that is sufficient to pull out the Fourier transform with great accuracy. If you do that, you will find this result, which I have not derived, but I'm telling you is a correct result. And that is this result, that these modes A omega dagger, if the 2-point function near the horizon is like that of flat space at very short distances, then these modes are occupied as if they're thermal modes, where this beta is given related to the surface gravity by 2 pi over kappa. Okay. So I didn't derive this result, but I hope at least that the result is clear. There's a question which is, how is it universal? It's universal in the sense that it only depends on the short distance behavior of the 2-point function. So as long as the short distance behavior of the 2-point function, so looks like the short distance behavior in flat space, which means it looks like 1 by geodesic distance to some power d minus 1 by 2, which is what it does in flat space. That is sufficient to derive this result. So what you really need here is just that the short distance behavior is fixed in terms of the short distance behavior of the 2-point function. Okay, is the statement of the result clear? The statement is, if you take these A omega prime operators, you smear them slightly in some formula that I wrote, just to make them normalizable so that the commutator looks like 1 rather than a delta function. Then you will find that the occupancy of these guys looks like this. Is the statement of the result clear? Because I went through this slightly fast and if there are questions, I'll be happy to answer them. If there are no questions, that worries me, because I find it hard to believe that Okay, I'll say it one more time just to be clear. If there are no questions, then I worry that no one. Yeah, there's a question. Yeah.
Yes, in fact, I have like two. First, I was not clear what is exactly inside the horizon and outgoing mode. What is this?
This has
I mean,
nothing to do with anything that's happening inside the horizon, first of all. This is only about the A modes, which only care about the A's and not about the A tildes. In fact, I could say something about the A tildes, but for now, I'm not going to say anything about the A tildes. This is just a property of the A's. What's happening inside the horizon are the A tildes. So I'm just saying the outgoing modes outside the horizon have the property that they are thermally occupied.
Yeah, but in fact, my question was like related to a slide before. I was just thinking, I didn't understand like what is the meaning of, because you say that inside the horizon we have ingoing and outgoing. I understand clearly what is the meaning of ingoing inside, but what is the meaning of outside? This yellow, yeah. What is the meaning of this outside mode?
These are just modes that travel. You see, if you look at waves, you can ask what is the direction of propagation of waves just by asking where are the lines of constant phase. So there are some modes that propagate parallel to the horizon. That's what we're calling outgoing. Inside, you're right, we shouldn't call them outgoing because these modes will eventually fall into the singularity.
Exactly, yeah.
These modes will eventually come out. So you can say, maybe your objection is to the use of the word outgoing. You're right, we shouldn't call them
exactly,
outgoing.
yeah, because they fall to the singularity.
Right. Thank you. Yeah, we should not use the word outgoing. So really, thank you for that. I was using outgoing, and that's slightly loose because they don't go out anywhere. I just meant that the modes outside are outgoing. They're the ones which propagate parallel to the horizon, and there are modes that propagate into the horizon. So the yellow modes or the orange modes are the ones which are propagating parallel to the horizon. So maybe
Correct.
the correct phrase is parallel and orthogonal to the horizon. Yeah.
Understand. Thank you. And the other question is like this definition you give for this mode A, the
Yes.
field phi, it's the field outside the horizon, right? It's
Is what the
It's the field phi that appear in the integral, the du
Yes.
phi. It's the field defined outside the horizon, right?
this field?
I mean, in the last slide. The last slide.
Yes.
Yeah. Sorry.
Yes. This is outside the horizon. Yes.
Okay.
Because it's minus u. Yes.
Thank you.
That's it. Yeah. Yeah. There's a delta. There's a delta. Oh, I should. There's an L. I could have written an L and L prime, and there would be a delta L prime. That's the other question that was asked. Yeah. The L independence of the correlator is not a manifestation of spherical symmetry. The spherical symmetry is coming in the fact that this is a delta L prime. However, there's something else that's happening, which is that this 2-point function doesn't care about L at all. Right? And that's a funny thing because, spherical symmetry doesn't tell you there should be a delta L prime, doesn't tell you the 2-point function doesn't care about L. This is a property of the fact that, all the modes inside of all different L's are occupied thermally, right? So it has to do with it has to do with the fact that this property of the wave equation that we discussed earlier, which is that in the wave function, the dependence on L just completely drops out. And so, it's really telling you that all modes at all angular momenta are occupied with this thermal occupancy, regardless of how high the angular momenta is. So that's not just a question of spherical symmetry, it's an additional aspect of the physics. What it has to do actually has to do with the fact that these correlators of the horizon, if you look at null correlators, they have the property of being ultra local. In that, if you look at correlators at very short distances, they turn out to be delta functions on the sphere. I don't have time to go into this right now, but that's what it's related to. And indeed, it's a fact that the occupancy doesn't depend on L. Okay. Great. Okay, good. Now, what about the B omega L modes? You see, so what did I say? What this is basically telling us, what's the physics? Let's say you're confused about what I said. The physics is just that the A omega L modes are thermally occupied. What I told you right now is that the A omega L modes are thermally occupied. That was the net result of all of these equations that we wrote down. So if you got lost in the equations, okay, and this is fixed, fixed by the short distance behavior across the horizon. Okay, that's the only thing you need to remember. Okay. What about the B omega Ls? If so, B omega Ls, in fact, you have a choice. If we put the B omega L in the vacuum, it's not fixed. Okay, so you can check that the behavior of the B omega Ls is not fixed. This is called the Unruh vacuum or the Unruh state. If you have what's called an eternal black hole, in which case there's also a past horizon, then you can't use the Unruh state. If you populate the B omega Ls thermally, that's called the Kruskal state. The Kruskal state. Okay. So for the B omega Ls, we actually have a choice of what to do, and we have different possible states. We will usually consider the Unruh state. Why will we consider the Unruh state? Because the Unruh state is a state where we are not throwing in matter from outside. You know, what are these different states for B omega L related to? They're related to whether we, after we form the black hole, do we continue to throw in matter from outside, or do we, create the black hole and then we don't throw in matter at late times? That's what the Unruh state corresponds to, where the B omega Ls in the vacuum. Remember, the B omega Ls are the things that are multiplying the ingoing modes. And so, if you say they're in the vacuum, then, that's the Unruh state where no matter is falling in at late times. Alternately, you could populate them thermally, and that would be called the Kruskal state. Yeah. Okay, great. So, you see, what is this telling us, right? What is the physics of what's happening here? The physics of what's happening here is that, so this was basically Hawking's calculation, right? So Hawking's calculation was to show that the A omega Ls are thermally populated. Okay? So this is the computation of Hawking radiation, okay, that I have summarized for you. What it tells you is that the black hole behaves physically. It tells us, implies that the black hole is like a thermal object And what is the temperature? Well, the temperature is fixed by this. If you look at this, this is the Boltzmann occupation number, right? And the temperature is fixed to be just the surface gravity over 2 pi. Okay. Now you can say more about this. You can put in the laws of black hole thermodynamics, and the fact that you fixed the temperature this way also tells you something about the black hole entropy, but we don't have time to go into that right now. But suffice it to say that it was already known even before Hawking that black holes obey some equation that looks like, if you take a black hole and you change it a little bit, they obey some equation that looks like this. Okay, and these were called the laws of black hole thermodynamics. This looks a lot like the first law of thermodynamics, plus work terms, which correspond to various charges and chemical potentials. And this looks a lot like the first law of thermodynamics, which also has the form du is equal to TdS plus work terms. And this law of black hole dynamics looks a lot like the second law of black hole, like the second law of thermodynamics, which tells you also that, the entropy always increases. So in the case of black holes, the law, this was something which was known earlier, was known that the area always increases. However, before Hawking's calculation, it was not clear how you should separate this into a T and an S. Because if somebody said A is S and kappa by 8 pi is T, I could say, no, I don't like that. I like A by 2 to be S. And, the two laws would still hold, because the fact that dA is larger than 0 also tells you dA by 2 is larger than 0. So Hawking's computation telling you that T was kappa over 8 pi allowed us to also say that S of the black hole is A over 4. Okay? And this is another well-known result, and in fact, can now be understood from a microscopic and statistical mechanics point of view. Okay, so this S parameter will appear a lot. It's the entropy of the black hole. I don't want to go into more details about how how these relations are derived and how it's understood microscopically, except to point out that the fact that black holes have a temperature also tells you they have an entropy, and that entropy is related to the area of the horizon by A over 4. Okay. Okay. So I realize that I have 15 minutes more. I'm running a little behind time. But let me now spend the remaining 15 minutes just introducing you to the first paradox, since this is a course on the information paradox. I now want to explain quickly how the simplest paradox that we're going to deal with comes from. Okay. So the simplest paradox is as follows. Right? Imagine an isolated black hole. Okay. What we have just computed tells us that the black hole, in fact, radiates some energy depending on the temperature of the black hole. And the reason it does that is because these modes are thermally occupied, right? Because they're thermally occupied, because the outgoing modes are thermally occupied, it tells you that if you were to take the back reaction of these modes and the geometry into account, these modes would carry away some energy, and therefore the black hole would lose mass. With what rate does it lose mass? Well, that's just the usual Stefan-Boltzmann law. Okay? And the rate is just minus C times area times T to the D plus 1. Okay? This is the area. This just comes from extensivity. This factor depends on what are called the gray body factors of the black hole. And it's not a physically very important it's not important for the paradox. It has to do with the fact that some of the radiation that is emitted, in fact, scatters off the black hole and falls back into the black hole. Okay? So there's some constant which is not important. There's the area, which has to do with the fact, as you might expect, that all parts of the black hole horizon radiate. And then there's a T to the D plus 1, which is basically just fixed by dimensional analysis. Remember, in 4 dimensions, this is a T to the 4. Okay. Let me also remind you that the mass of the black hole, okay, was proportional to RH to the D minus 2. This was one of the first formulas we wrote down. If you work out what the temperature is proportional to, remember the temperature is proportional to the surface gravity. You can work out, that's just the derivative of f of r, remember, f prime r at r equal to RH. You will find that the temperature is proportional to 1 over the horizon radius. And this is a pretty universal kind of result. The area is proportional to RH to the D minus, RH to the D minus 1. Right? In terms of the horizon radius. And therefore, this equation, which is telling you the loss in energy, you can think of as dRH by dt is proportional to minus 1 to the RH to the D minus 1. What does this tell you? This tells you that in a time at the beginning of this lecture, we had this thing which was called the evaporation time. It tells you that in an evaporation time of the order of RH to the D, which you can think of as being proportional to area over the temperature, okay, RH becomes 0. So if you start with a black hole with some horizon radius, after this much time, the formula for Hawking radiation that I showed, that I quoted and briefly indicated how it would be derived, tells you that the black hole will completely evaporate and will leave you with nothing in a time that's proportional to the area divided by the temperature. Okay. Notice that the radiation is not actually constant. Right? In fact, the radiation, the temperature increases as the black hole becomes smaller. That's because the temperature is proportional to 1 over RH. So the black hole doesn't radiate at a constant rate. And its last stages look a little bit like an explosion where the black hole just explodes. Okay? But the key point is that after a finite amount of time, the black hole just completely evaporates and nothing is left. Okay? Is this physics clear? Okay, so what is the black hole information paradox, right? What is the simplest way to understand the black hole information paradox? The simplest way to understand the black hole information paradox is that the formula that we derived, remember the formula that we derived, which said A omega L times A omega L dagger times delta LL prime, did not care about the initial state of the black hole. Why did it not care about the initial state of the black hole? Because it just cared about the short distance behavior of the physics near the black hole horizon. Okay? So the simplest version of the information paradox is simply that the outgoing flux is independent of the details of the initial state. That's the simplest version of the information paradox. Okay? And that is a paradox because, and I'll say this a little bit more precisely in the next lecture, but without introducing unnecessary equations, it's a paradox because you can start with star 1. Okay? Maybe this has, high helium. Okay, it has a lot of helium. It forms a black hole. And the black hole radiates. What does the radiation care about? It cares about beta. So it cares about the surface gravity. So it cares about the mass. Right? It forms some radiation. You can think of a star 2. Maybe it had low helium or it had some other properties. Right? It also forms a black hole. But maybe if you ensure that the two stars have the same mass to start with, they'll have the same temperature when this black hole forms. And therefore, they will give rise to the same radiation after the black hole has evaporated completely. Now, this kind of process is in violation of a very fundamental principle of physics, which is the reversibility of time evolution. So in physics, time evolution is always reversible. If one keeps track of microscopic details. Okay. Here we might have thought that we kept track of what the quantum fields were doing, and therefore it should be the case that the time evolution of the black hole was reversible. But instead, we seem to be finding that this radiation that's emitted is independent of everything in the initial state, and therefore it looks like the time evolution is not universal. Okay, so this is what I gave you right now is the simplest version of the information paradox. It's also the simplest version to resolve. So next time, what I'll do is I'll just rephrase what we just derived slightly more precisely and explain this paradox in a slightly more precise way. And then also explain how this paradox that I currently presented can be resolved rather straightforwardly by just invoking some simple principles of statistical mechanics. But I don't want to go into that right now because we just have about 5 or 10 minutes left. So instead, I thought I'll stop here and just pause for questions. Let me just recap the last part of what I said. Okay. So the last part of what I said was, we derived this fact that this A omega dagger had some thermal occupancy. It was universal. It was fixed by the short distance behavior of the 2-point function. This tells you, that the black hole looks like it's radiating some energy with a temperature which is given by kappa over 2 pi. This combined with other laws of black hole dynamics that I haven't derived, but which were known earlier, and hopefully you've seen in your GR course, tells you can associate an entropy with the black hole. That's fine, but it also tells you something slightly else, something different. And that is, it tells you that, if you were to take into account the back reaction of the radiation on the geometry, then because energy is conserved, if there's some energy which is being lost to radiation, then there must be, the black hole itself must lose energy. And therefore, the black hole itself must lose mass. At what rate must it lose mass? Well, it must lose mass. You can just integrate the total flux of energy that comes out. Dimensional analysis tells you it should be proportional to t to the power d plus 1 into the area, just because it's extensive. There's a numerical factor c, which you can't compute just by dimensional analysis. It depends on the details of the geometry. It's not very important. The basic fact is that this tells you that the radius of the black hole goes down at a rate that's given by 1 by r to the d minus 1. In fact, as r becomes small, this rate becomes faster. And at the beginning of this lecture, we introduced this notion of an evaporation time. And what this tells you is that if you integrate this equation, if you start with some initial RH, then in a time which is given by RH to the d, the black hole completely evaporates away. Okay. And, oops, what is this? Black hole completely evaporates away. And the salient feature of the radiation that we derived was that, it didn't depend on the details of the star or the black hole or the initial state. And therefore, it looks like this leads to a paradox. I'll just answer the questions in a minute, because it seems that you can start with two different stars, form black holes. If the stars have the same mass, you get the same radiation at the end. And that looks like it violates the reversibility of time evolution. Okay, so that's what I want to say. I see there's some questions, and I can answer those questions, and then we can stop. Yeah. So I see a question in the chat. Let me answer that. Will the long distance correlators and non-universal terms care about the details of the state? Yeah. So you see, the thing that we wanted to derive was, in fact, what was the occupancy of the modes, right? And the occupancy of the modes, in fact, just cares about the short distance behavior of the correlators. So this is the statement that Hawking radiation is pretty universal. The fact that you get thermal radiation from the black hole doesn't depend on many details of the geometry or the interaction and so on. That's why Hawking radiation is such a universal result. And it really cares only about what's happening close to the horizon. Okay? So of course, there are long distance correlators that you can look at, but this result is a very universal and it's a very robust result. And it doesn't care about, what's happening elsewhere in the geometry. However, this result, telling you that the correlators are thermally populated at the horizon, that these modes are thermally populated at the horizon, is enough to lead you to the conclusion that the black hole is going to evaporate away entirely. Now, you could say, what about the rest of the details of the geometry? Well, they are important. It's not like they're not important. They'll control this factor C, right? So it's true that, even if you have some thermal temperature at the horizon, maybe you go far away and, some of it bounces back. How much of it bounces back depends on the geometry and so on. But as long as you have a minus sign here and, the rest of the result just follows from dimensional analysis, that's why I wrote proportional here. So you could, the precise constants of proportionality would depend on the details of the geometry. But the fact that the black hole will evaporate away entirely is rather robust and doesn't care about the details of the geometry far away from the horizon. Yeah. Why is time evolution being reversible something that we take as a necessary principle? Because you see, that's a very fundamental principle of quantum mechanics. If you look at the Schrodinger equation, it tells you that the state evolves with this is a unitary operator. So it can always be reversed. Okay. So you can always go from, if this is u, you can take psi to u psi. And if you know u psi, you multiply it with u dagger, you get back psi. So, in physics, information is never lost. This is also true in classical physics. It's a property of classical physics. There are some differential equations, and those differential equations are always reversible. So if quantum mechanical time evolution is unitary, then time evolution would be reversible. Indeed, Hawking's proposal was maybe it's not unitary in the presence of black holes. That's not how we think of things now. But that was the proposal that Hawking had. Okay, but the usual idea would be that quantum mechanical evolution is unitary. I see somebody had a question, but yeah. Does that answer this question? Both the questions that were asked? Okay. Yeah, Harpreet, I think, has a question.
Sir, the means mode we are used just to compute this spectra means it contain a part of the wave function, isn't it? It has only a mu mode, means the total wave function means total size.
Huh.
There are other parts also.
Yeah. The other parts are the parts which are specifying data here. You see, if you think of what's happening to the black hole, I'll say this in more detail later. These B modes are, you can, so you're right, there's some horizon here, right? And the horizon, there's some data on the horizon which corresponds to these B modes, but you can think of those B modes as setting the initial condition. If you think of the whole geometry, there's some final state which is determined by what's happening on Scry plus at very late times, and there's some initial state. So those other modes you can think of as what's happening with the initial state. And what Hawking computed was, regardless of what you do with the initial state and how you throw in. So let's say you set that in the vacuum. So you have some black hole which forms, and after that you don't throw in some matter. Then that's the statement that the B modes are in the vacuum. Okay? If you don't want to put them in the vacuum, that's the statement that you're throwing in some matter. You can decide to do that. But what Hawking's point was, regardless of what you do, the final state, which is specified just on this region, this is the out state. This out state is thermally occupied. And indeed, when the black hole completely evaporates away, then this is the only radiation that remains. The only thing that remains is the radiation, right? And so the only modes that you need to keep track of at very late times are these A modes. Those are the modes which are outside the horizon. And if those are thermally populated, that Hawking said gives you a complete description of the state. I mean, the main point is this, that, it is true that at intermediate times you might ask, there's a horizon, there's something here. But after the black hole has evaporated away, what remains is just these A modes. That's the energy that was radiated out. And, so that's, if you know the state of those, it seems like you know the whole state of the world, and that looks like it's thermal. Is that clear? Was it clear or not? I'm guessing it was clear if you don't follow up.
Yeah, yes, it's clear.
Okay. Are we assuming the black hole remains static? No, it didn't remain static. You could have asked, in the derivation that we did, it's true the derivation was a quasi-static derivation. So, we did a derivation assuming that there was a time translational symmetry, and then we applied it to a time-dependent situation. So it's true there are corrections that we need to be careful of there. We don't expect that those corrections will change the leading order form of the result, although you're right, they would change. This temperature is not really a system in equilibrium. Whereas the result we got was an equilibrium result. And so you're right, there are corrections to that. It's not generally expected that those corrections will change things, because an order of magnitude estimate would suggest that, the evaporation time is a very long time compared. You see, the temperature is compared to the light crossing time of the black hole, right? It's given by the radius of the horizon. The evaporation time is much, much longer than that. As a result, you expect that the corrections you get to this quasi-static or to this, by assuming this thing is in equilibrium, are very small. And therefore you believe that, you can apply for the black hole for short periods of time, this equilibrium approximation. It's true, of course, over long periods, the radius of the horizon changes. That's why in this differential equation that we derived, I kind of assumed that this was being followed, it was, this temperature was changing as a function of time. But I was assuming that, for times which are much longer than RH, this temperature can be assumed to be constant, and then you change it. So it's true we're applying some quasi-static approximation, but we believe that's justified. There's a molecular chaos argument they're used to justify why time reversal symmetry is lost. Yeah, so indeed there's this, we'll find next time that there's a simple statistical mechanics argument that tells us why time reversal symmetry is lost. So indeed what's happening here is very similar to how we see dissipation in ordinary systems. You throw a ball and it looks like it stops. Why does it stop? Because the information went into some details of the material that you didn't keep track of. And indeed, next time I'll explain how there are some microscopic details that we did not keep track of and how those are sufficient to restore unitarity. So this is just fixing the simplest version of the information paradox. I'll explain more sophisticated versions next time. but it's not unrelated. It's very similar to what happens in ordinary statistical mechanics, where it looks effectively that systems are dissipative, even if they're not. Okay. Now, another question is, how does this correlate to pair production explanation? This correlates to pair production explanation because I gave you the answer occupancy for the A omegas. In fact, I didn't tell you what was happening to the A tilde omegas. It turns out that the A tilde omegas, which are the modes which are behind the horizon, are also going to be occupied in this way. Okay? So, that's the pair production explanation. And in fact, it turns out that if you compute A omega L, A tilde omega L, where A tilde omega L is defined behind the horizon, that picks up some form that looks like this. Okay. So the modes in front of the horizon and the modes behind the horizon are entangled. Okay, and they have some universal form of entanglement. So I didn't write down this formula, and similarly for A dagger omega and A dagger tilde omega L. This is where the pair production explanation comes from. I didn't explain this because I didn't have to say anything about what the A tilde omega modes are doing for the purpose of setting up the simplest paradox. For some other more refined versions of the information paradox, this entanglement is important, and this is the precise version of the pair production explanation, which is that the modes outside are entangled with the modes inside. There's a specific 2-point correlation function which is given by this. Okay, are there other questions?
Yeah, I have a question maybe related to a previous question asked.
Yeah.
So I want to understand really the process of this, why we say that it's a kind of radiation. When we compute this occupancy of A mode, we took into account only outgoing mode, but outside the horizon. So the
Yes.
phi was
Yes.
phi. Why
Yes.
I understand this as a radiation, because I guess that I'll say that it's a radiation if the field was inside at some time, but in this case, A correspond to the phi.
Well, you have to think of an observer who's sitting here, right? So an observer who's sitting here will see eventually these red modes come and hit the observer. So,
Yes.
for an observer outside, it looks like, you have some thermal modes which are coming and hitting the observer. That's why it's called radiation. It doesn't, observer outside doesn't care, is it coming from inside or outside, or is it at the surface or a little bit outside the surface or so on, right? They see some black hole and they see this thing coming and hitting the black hole.